Now, in this lecture, I will answer on two questions. In the first question, we find out the radius of this circle that is described by triangle ABC. In the second question, we find out the area of this rectangle ABCD that blocks this circle. We start with the first question. We solve the first question in two different methods. So in the drawing, we have triangle ABC, side BC of triangle ABC equals to 2 units, angle ABC equals to 60 degrees, angle ACB, this angle equals to 75 degrees, and our mission is to find out the radius of this circle that is described by triangle ABC. So we start with the first method. In the first method, from point C, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle is equal also to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. In the next step, we'll copy the right green triangle ABD in a new page and we'll analyze triangle ABD. It is actually triangle PDC. This is the right triangle DBC that I copied from the original drawing. You know that the sum of the angles inside triangle DBC must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So each angle we have here, this angle equals to 60 degrees, plus this angle that is equal to 90 degrees, plus the missing angle that we define as angle X. In total, the sum of those three angles must be equal to 180 degrees. We subtract here 60 degrees plus 90 degrees is 150 degrees, plus the size of angle x. In total they must be equal to 180 degrees. Here we subtract 150 degrees from this equation and we get that the missing angle x is equal to 180 degrees minus 150 degrees. It is equal to 30 degrees. So this angle equals to 30 degrees. You can write here also angle DCB equals to 30 degrees. We will continue to focus on the right triangle, triangle DCB. On the right triangle, triangle DCB, it is very easy to see from the drawing that sinus 30 degrees is equal to dB over BC. Okay? Sinus 30 degrees is 1/2. So 1/2 equals to dB over BC, but BC equals to 2 units according to what is given as the question, so we substitute BC by 2. So we got that 1/2 equals to dB over 2. We multiply this equation by 2 and we get that dB equals to 1 unit. You can write here that dB equals to 1 unit. We continue to focus on the right triangle, triangle DCB or DBC. In the right triangle DBC, it's very easy to see from the drawing that cosine 30 degrees is equal to DC over BC. Okay, DC over BC. So cosine 30 degrees equals to DC, and BC is 2, so it is DC over 2. Cosine 30 degrees is equal to square root of 3 over 2. So square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and we will get that DC is equal to square root of 3 units. Here, DC is equal to square root of 3 units. In the next step, we will find out the size of this angle. This angle equals to the size of the big angle, that is angle ACB, minus the size of the small angle, that is equal to angle DCB. The big angle ACB equals to 75 degrees, minus the small angle that is equal to 30 degrees. 75 degrees minus 30 degrees is equal to 45 degrees. Okay, angle ACD equals to 45 degrees. In the next step, I will copy the right triangle, triangle ADC in a new page, and we will analyze triangle ADC. Side DC equals to square root of 3 units. Angle ACB, this angle equals to 45 degrees. So 3, this is the right triangle, triangle ADC, that I copied from the original drawing. The sum of the angles inside triangle ADC are equal to 180 degrees. So which angles we have inside triangle ADC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus the missing angle, this angle we define as x. In total, the sum of those three angles must be equal to 180 degrees. So here 90 degrees plus 45 degrees is equal to 135 degrees, plus the size of angle x. In total, it must be equal to 180 degrees. So here we subtract 135 degrees from this equation, and we get that the missing angle, angle x, equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. So this angle, angle x, equals to 45 degrees. We continue to focus on the right triangle, triangle ADC. In the right triangle, triangle ADC, those two angles are both equal to 45 degrees, therefore they are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So in front of this angle we have side AD. In front of this angle we have side DC. And according to the rule that I mentioned, those two sides that are located in front of equal angles must be also equal to each other, so AD equals to DC. But according to what we have already found out, that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to square root of 3 units, we will derive that AD is also equals to the square root of 3 units. Here AD equals to the square root of 3 units. And you can write here that AD equals to the square root of 3 units. Okay. In the next step, we will implement the Pythagoras theorem on this right triangle, triangle ADC, in order to find out the length of the hypotenuse AC. So here, by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse is AC, and the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD squared plus DC squared. Okay, so here AC squared must be equal to AD square. AD is equal to square root of 3 units, therefore AD square is square root of 3 squared, that is 3, plus DC square. DC is equal to square root of 3, therefore DC square is square root of 3 squared, that is 3. So in conclusion, we found out that AC square is equal to 3 plus 3, that is 6. Here we take a root out of this equation, equation number 1, and we get that AC is equal to the square root of 6 units. Yeah. So we found out that AC equals to the square root of 6 units. Yeah, AC equals to the square root of 6 units. So actually we have all the lengths of sides of triangle ABC. In the next step, I will present to you a new formula that gives us the radius of this circle that is inscribed by triangle ABC. The radius of any circle that is inscribed by triangle ABC, or by triangle ABC that could be any triangle, it is equal to the area of the triangle that blocks the circle. In this case it's triangle ABC, over the semi-perimeter of triangle ABC. Okay? We can implement rule number 7 in our drawing. According to the new formula, the radius of this circle that is inscribed by triangle ABC the radius R will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. And the semi-perimeter of any triangle is equal to the perimeter over 2. So the radius of our circle, this circle that is inscribed by triangle ABC, will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. Okay, so what is the area of triangle ABC? The area of triangle ABC is equal to the base of the triangle times the height to the base over 2. Okay, so the area of triangle ABC is equal to the base of the triangle ABC. We take the base as AB. If the base is AB, then the height to the base that creates 90 degrees with the base is CD over 2. So in conclusion, I found out that the area of triangle ABC is equal to the base of triangle ABC that is AB times the height of the base that is CD over 2. Okay, so the area of triangle ABC is equal to the base AB. The base AB equals to 1 plus square root of 3 units times the height of the base that is DC, and DC equals to square root of 3 units over 2. Okay, and the value of this expression, 1 plus square root of 3 times square root of 3 over 2, is equal to 2.366 per unit. So we found out that the area of triangle ABC is equal to 2.366 square units. In the next step, we'll find out the semi-perimeter of triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2, and the perimeter of triangle ABC is equal to AB plus BC plus AC, and if we divide the perimeter by 2, we'll get the semi-perimeter of triangle ABC. So the semi-perimeter of triangle ABC is equal to AB is equal to 1 plus square root of 3 units plus BC is equal to 2 units plus AC it is equal to square root of 6 units, all divided by 2. Okay, in total this expression equals to 3.59 units. So the radius, so S equals to 3.59 units. So the radius of this circle that is described by triangle ABC according to the new formula will be equal to the area of triangle ABC, that is equal to 2.366 square units over, so here I write down the formula for the radius according to the new formula. It is equals to the area of triangle ABC over the semi-perimeter of triangle ABC. Okay, and the so here I repeat again, the radius of the circle that is described by triangle ABC equals to the area of triangle ABC, that is equal to 2.366 square units over the semi-perimeter of triangle ABC, that is equal to 3.59 units. So the radius 2.366 over 3.59 is equal to 0.6589 units. So the radius of the circle of our circle that is inscribed by triangle ABC equals to 0.6589 units. Okay. The radius of this circle that is described by triangle ABC equals to 0.6589 units. So we finish with the first method. In the next step, I'll present to you how to find out the radius of this circle that is inscribed by triangle ABC according to the second method. In the second method, we define the center of this circle as point O, it's O. We define the point of tendency of tangent BC with this circle as point D. We will join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle that we will define as R. So here we have the radius OD that is drawn to the point of tendency, and according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Okay, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1, because the radius of M it is drawn to the point of tendency. So here also point D is the point of tendency and the radius OD it is drawn to the point of tendency, therefore according to rule number 1 this angle equals to 90 degrees and this angle it is also equals to 90 degrees. Okay. We join points O and B together by a straight line. We join points O and C together by a straight line. We will define the point of tendency of tangent AB with this circle SE, and we define the point of tendency of tangent AC with this circle SF. We join points O and D together by a straight line. So here point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of the circle that is equal to R. E is the point of tendency of tangent AB with this circle, so here the radius OE is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be equal to 90 degrees. We join points O and F together by a straight line. So here, point O is the center of the circle, point F is the point of the circle itself. Therefore, OF is the radius of this circle that is equal to R. And we have the radius OF that is drawn to point F, that is the point of tendency of tangent AC with this circle, therefore according to rule number 1 this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so here I present to you also rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. From the common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA is equal to PB. you can implement rule number 2 in our drawing, because if we focus on the common external point, point B, from the common external point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they must be equal to each other. That is to say, BD is equal to BE. Likewise, if we focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle, tangent CD and tangent CF. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, CD is equal to CF. Okay, so in the next step, we prove that the green triangle OBD is congruent to the orange triangle OBE. So I write it down. We'll actually prove that the green triangle OBD is congruent to the orange triangle OBE. So why those two triangles congruent to each other? First of all, we just right now prove that side BD of the green triangle is equal to side BE of the orange triangle according to rule number 2. So here you can write down that BD is equal to EB according to rule number 2. In addition, DO equals to OE. They are equal to each other because of the fact that they are both the radii of the circle that is equal to R. And finally, side BO is a common side that belongs to both triangles, so side BO is equal to itself. It's a common side that belongs to both triangles. So, actually prove that the green triangle is congruent to the orange triangle according to side rule. So I write it down. Triangle OBC is congruent to triangle OBE according to side rule. And from the fact that those two triangles can go into each other, we will derive that those two angles are equal to each other. That is to say, angle OBD in the green triangle is equal to angle OBE in the orange triangle according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. And if we define this angle OBD as alpha, then from this equation angle OBD equals to angle OBE equals to alpha, we will derive that angle. Actually, if we define angle OBE as alpha, then from this equation angle OBD equals to angle OBE equals to alpha, we will derive that angle OBD, this angle, is also equals to alpha. So those two angles, they are both equal to alpha, and the sum of those two angles is alpha plus alpha, and according to what is given as the equation, alpha plus alpha is equal to 60 degrees. Alpha plus alpha is 2 alpha, so 2 alpha equals to 60 degrees. We divide the equation by 2 and we get that alpha equals to 60 degrees over 2 is 30 degrees. So we found out that alpha equals to 30 degrees, therefore we can write down here that angle alpha equals to 30 degrees, this angle alpha equals to 30 degrees, and this angle alpha equals to 30 degrees. Likewise, it is very easy to prove that those two triangles also can go into each other according to side rule, and therefore those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. That is to say, angle OCF, this angle, is equal to this angle that is actually angle OCD, and if we define angle OCD as theta, then from this equation angle OCF equals to angle OCD equals to theta, we derive that angle OCF is also equals to theta. Angle OCF is also equals to theta. So actually, I found out that both those two angles are equal to theta, and the sum of those two angles is theta plus theta, that is 2 theta, and 2 theta equals to 75 degrees according to what is given us in the question. Okay, so here we divide this equation by 2, and we get that theta equals to 37.5 degrees. Here, angle theta equals to 37.5 degrees, and here also angle theta equals to 37.5 degrees. In the next step, we will focus on the green triangle, triangle OBD. In the green triangle, triangle OBD, it is very easy to see from the drawing that tangents 30 degrees is equal to OD over BD. Again, tangents 30 degrees equals to OD over BD. OD equals to R, so we substitute OD by R. So here we found out that tangents 30 degrees equals to R over BD. Here we will multiply this equation by BD, and then we will divide it by tangents 30 degrees, and we will get that BD is equal to R over tangents 30 degrees. Okay, so I found out that BD equals to R over tangents 30 degrees. In the next step, we will focus on the yellow triangle, triangle OCD. In the yellow triangle, triangle OCD, tangents 37.5 degrees is equal to OD over DC. OD equals to R, so we substitute OD by R over DC. So in conclusion, I found out that tangents 37.5 degrees is equal to R over DC. I'll repeat again. tangent 37.5 degrees equals to r over dc. We will multiply this equation by dc and then we will divide it by tangent 37.5 degrees and we will get that dc is equal to r over tangent 37.5 degrees. Okay. So we actually found out the values of DC and the value of PD. And what is the value of side BC of triangle ABC? We know that it is equal to 2 units, but BD is also equals, BC is also equals to BD plus DC. I write it down. BC is equal to BD plus DC. Repeat again. BC is equal to BD plus DC. So BC is equal to BD. We have already found out that BD equals to R over tangent 30 degrees plus DC. We already found out that DC equals to R over tangent 37.5 degrees. We know that BC equals to 2 units. So we substitute BC by 2 as 2 equals to, here we take R as a common factor. What is left from R over tangent 30 degrees? After we took from it R as a common factor, what is left is actually 1 over tangent 30 degrees. And what is left from R over tangent 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over tangent 37.5 degrees. So here we found out that 2 equals to R and 1 over tangent 30 degrees equals to 1.732 plus 1 over tangent 37.5 degrees. It is equal to 1.303. So here 2 equals to R and 1.732 plus 1.303, it is equal to 3.035. So we divide this equation by 3.035 and we will get that the radius that we are looking for is equal to 2 over 3.035. 2 over 3.035, it is equal to 0.6589 units. So we found out that the radius of the circle according to the second method, it is equal to 0.6589 units. In both methods we arrive to the same result. In the next step, I present to you the second question and we will solve the second question in 2 different methods. So in the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle that is blocked, a circle that is described by rectangle ABCD. Chord PS equals to 6 units, line segment SQ equals to 5 units, and our mission is to find out the area of this rectangle ABCD. We start with the first method, and we actually know that all the angles inside the rectangle are right angles, therefore this angle is equal to 90 degrees, this angle equals to 90 degrees, this angle is equal to 90 degrees, and this angle, it is also equal to 90 degrees. We will define side AB of rectangle ABCD as A. AB equals to A. We will define side BC as B. We know that BC is also the diameter of the circle, so I will write it down. B is the diameter of the circle. It's very easy to prove it, but we will not prove it in this lecture. And here we define the center of this circle as point O, and I will present to you rule number 4, and we will implement rule number 4 in our drawing. According to rule number 4, the perpendicular from the center of a circle to a chord bisect the chord. Here, point O is the center of the circle, and the perpendicular from the center of the circle is OM. The perpendicular OM bisects chord CD. That is to say, CM equals to MD according to rule number 4. Again, the perpendicular from the center of the circle, that is OM, bisects CD. That is to say, CM equals to MD according to rule number 4. So we'll implement rule number 4 in our drawing. From the center of this circle, that is actually point O, we will draw perpendicular on chord SP. So actually, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and SP as M. And according to rule number 4, the perpendicular OM bisects chord SP. That is to say, SM equals to MP. SM equals to MP according to rule number 4. So if we define SM as X, here if SM equals to X, then from this equation we will derive that MP is also equals to X. MP equals to X. And what is the length of chord SP? Chord SP equals to SM plus MP. That is to say, chord SP equals to SM, that is X, plus MP, that is also X. So in conclusion, SP equals to X plus X. SP equals to X plus X. So SP equals to X plus X, that is 2X. And according to what is given us in the question, SP equals to 6 units. So we can write here that SP equals to 6 units. And from this equation, SP equals to 6 equals to SP equals to 2X. We derive that 6 equals to 2X. We divide this equation by 2 and we get that X equals to 3 units. Okay, here X equals to 3 units. X equals to 3 units. And here also X equals to 3 units. Okay. We define the point of tendency of tangent CD with this circle as point F. We join points O and F together by a straight line. point O is the center of the circle. Point F is the point on the circle itself. It is also the point of tendency of DC of the circle. Therefore, OF is the radius of the circle. That is equal to R according to our definition. So we have here the radius OF that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, we join points O and P together by a straight line. Here, point O is the center of the circle. Point P is the point of the circle itself. Therefore, OP is the radius of this circle that is equal to R according to our definition. So if the radius of the circle is equal to R and the diameter of the circle is equal to B, it means that the radius is equal to half of it. That is to say, the radius equals to B over 2. It is half of the diameter that is B. So here we have the radius of B that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So here we created quadrilateral OP FC. Inside quadrilateral OP FC, we have 1, 2, 3 right angles. And any quadrilateral that has 3 right angles, the fourth angle, this angle, must be also equal to 90 degrees because of the fact that the sum of the angles in any quadrilateral is equal to 360 degrees. And in order to complete the sum of the angles inside this quadrilateral OP FC to 360 degrees, this angle must be equal to 90 degrees. Okay, so in the next step, from point Q, we will draw perpendicular on BC. I repeat again, from point Q, we will draw perpendicular on BC. So here, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC is T. We define the intersection point between perpendicular QT and the radius OF as L. So here we actually created quadrilateral QP LT inside quadrilateral OP LT. Inside quadrilateral OP LT, we have 1, 2, 3 right angles. Again, inside quadrilateral OP LT, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. This angle must be equal to 90 degrees. So actually, inside quadrilateral OP LT, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral OP LT, this quadrilateral, as a rectangle. Okay? Quadrilateral OP LT is a rectangle. I repeat again, quadrilateral OP LT is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other. That is to say, in rectangle OPLT, side OP is parallel to side LP. LT, side OP is parallel to side LT. OP is parallel to LT. I repeat again, in rectangle OPLT, side OP is parallel to side LT according to the rule that the opposite sides of a rectangle are parallel to each other. And what is LT is one side of rectangle of LT, but LT it is also part of perpendicular QT. Repeat again, LT is part of the perpendicular QT. And QT is a perpendicular, it is absolutely a straight line. QT is a perpendicular, it is absolutely a straight line. So I write it down that QT is a straight line. QT is a perpendicular, is a straight line. And so the straight line, so LT is part of the straight line QT. Again, LT is part of the straight line QT, and LT is parallel to OP. And if part of the straight line, that is LT, is parallel to OP, it means that the straight line itself, QT, must be also parallel to OP. So I can write down that QT must be also parallel to LT. Why? Because if a part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, QT is parallel to LT. And we have here rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Repeat again. According to rule number 9, alternating angles between parallel lines are equal to each other. Here, line A is parallel to line B, and the two pink angles are defined as alternating angles and they are located between the parallel lines A and B, therefore A and B, therefore they are equal to each other. We can implement rule number 9 in our drawing, because in our drawing those two angles are defined as alternating angles and they are located between the parallel lines OP and QT, therefore they are equal to each other according to rule number 9. So we can write down that angle OPQ, this angle OPQ is equal to this angle, that is actually angle PQT. Repeat again. Angle OPQ equals to angle PQT according to rule number 9. So if we define angle PQT as theta, angle PQT equals to theta according to our definition. Angle PQT equals to theta according to our definition. Then from this equation, angle OPQ equals to angle PQT equals to theta, we will derive that angle OPQ is also equals to theta. Okay, angle OPQ, this angle OPQ is equal to theta. Okay, this angle equals to theta. And right here that this angle equals to theta. Okay. In the next step, we'll focus on quadrilateral QTCD. On quadrilateral QTCD, we have 1, 2, 3 right angles. Again, in quadrilateral QTCD, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. This angle must be also equal to 90 degrees. So actually, we found out that Inside quadrilateral QTCD, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral QTDC as a rectangle. Quadrilateral QTDC is a rectangle I repeat again, quadrilateral QTDC is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, QT is equal to DC. QT is equal to DC. QT is equal to DC. But we know that ABCD is a rectangle and the opposite sides of rectangle ABCD are equal to each other. That is to say, DC equals to AB. Okay, DC equals to AB because of the fact that ABCD is a rectangle. So from this equation, QT equals to DC equals to AB, we will derive that QT is also equals to AB. QT is equals to AB. But according to our definition, AB equals to A. Yeah, AB equals to A according to our definition. And from this equation, QT equals to AB equals to A, we will derive that QT is also equals to A. QT is also equals to A. So, found out that QT equals to A. In the next step, we will focus on the right triangle, triangle OMP. So I will copy triangle OMP in a new page and we will analyze triangle OMP. Side MP equals to 3 units, and the hypotenuse OP equals to B over 2. Angle OMP, angle OPM, this angle equals to theta. So this is actually the right triangle, triangle OMP that I copied from the original drawing. In this triangle, triangle OMP, cosine theta equals to MP over OP. Again, cosine theta equals to MP over OP. So I write it down. MP equals to 3 units, so we substitute MP by 3, and OP equals to B over 2, so we substitute OP by B over 2. 3 over B over 2, what is the value of 3 over B over 2? We'll move to the numerator, 2 times 3 is 6, we'll move B to the denominator, so we get here 6 over B. So in conclusion, according to equation number 1, we found out that cosine theta equals to 6 over B. Okay. In the next step, we'll focus on the right big triangle, triangle PQT. On the right big triangle, triangle PQT, it is very easy to see from the drawing that cosine theta is equal to QT over QP. Cosine theta equals to QT over QP. Repeat again. The right triangle QPT, cosine theta equals to QT over QP. QT equals to A, according to what we already found out, so we substitute QT by A. And QP or PQ equals to 5 plus 6, that is 11. And again, QP equals to 5 plus 6, that is 11, so we substitute QP by 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. While according to equation number 1, we found out that cosine theta is equal to 6 over B. So we have two different expressions for cosine theta. Therefore, we create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 is equal to 6 over B, and it must be equal to cosine theta according to equation number 2, that is equal to A over 11. So according to equation number 3, we found out that A over B equals to A over 11, 6 over B equals to A over 11. Here we cross multiply this equation, equation number 3, and we found out that according to equation number 3, A times B equals to 6 times 11, that is 66. So we found out that AB equals to 66. What is the area of rectangle ABCD? The area of rectangle ABCD is equal to the length of the rectangle times the width of the rectangle. The length of rectangle ABCD is equal to AB, and the width is equal to CD. And according to our definition, AB equals to A, and B, and it is AB times BC. Repeat again. The length is AB, and the width is BC. The length AB equals to A according to our definition, and the width BC is equal to B according to our definition. So in conclusion, we found out that the area of rectangle ABCD equals to A times B. We just right now found out that A times B is equal to 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of rectangle ABCD according to the second method. We know that all the angles inside the rectangle are right angles. Therefore, this angle equals to 90 degrees. This angle equals to 90 degrees. This angle equals to 90 degrees. And this angle is also equals to 90 degrees. As we did in the first method, we will define side AB as A, we will define side BC as B. I've already explained to you that BC is also the diameter of the circle, so I write it down. We define the center of the circle as O. We join points O and P together by a straight line. P is the point of tendency of tangent BC with this circle. Point O is the center of the circle. Point P is the point of the circle itself, therefore OP is the radius of the circle that we define as R. If the diameter is B and the radius is R, then it means that the radius of the circle must be equal to half of the diameter, that is to say it must be equal to B over 2. And we have here the radius of P that is bound to the point of tendency. Therefore, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. In the next step, we will extend we'll extend the radius PO until it intersects with side AB of rectangle ABCD, and we'll define the touching point of the extended radius PO and side AD of rectangle ABCD as T. So inside quadrilateral ABTP, we have 1, 2, 3 right angles. And therefore, the fourth angle must be also equal to 90 degrees. So quadrilateral ABTP has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral ABTP as a rectangle. Quadrilateral ABTP is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side TP. AB equals to TP, but according to our definition, AB equals to A. And from this equation, A equals to AB equals to TP, we will derive that TP is also equals to A. TP is equal to A. Here, TP equals to A. Okay, we focus on quadrilateral TPDC. Inside quadrilateral TPDC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. This angle is the right angle, it is equal to 90 degrees. We define the touching point of the extended radius PO and the circle as point L. We join points L and S together by a straight line. What is the definition of chord LP? Chord LP passes through the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, LP is the diameter of the circle. LP is the diameter of the circle, and the diameter of the circle is equal to B. So here, by joining points L and S together by a straight line, we created here peripheral angle LSP. This angle is a peripheral angle, angle LSP. And we actually have rule number 5 that talks about peripheral angle that rests on the diameter of the circle. According to rule number 5, any peripheral angle that rests on the diameter of a circle must be equal to 90 degrees. Here we have peripheral angle AMB that rests on AB, that is the diameter of the circle, and therefore it is equal to 90 degrees. This peripheral angle equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle LSP. This peripheral angle rests on NP, that is the diameter of the circle. Therefore, according to rule number 5, this angle, it is a right angle, it is equal to 90 degrees. In the next, so here we define angle LPS as theta. This angle equals to theta. So if we focus on the right triangle, triangle LSP, this angle equals to 90 degrees. This angle equals to theta. Therefore, this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta equals to 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. That is the sum of the angles in any triangle. We focus on the right triangle, the right big triangle, triangle TPQ, the right big triangle. This angle equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta. So in the next step, we prove that the green small triangle, triangle LSP is congruent, is similar to the big right triangle, triangle TPQ. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down. Angle TQP angle TQP is equal to this angle, that is actually angle SLP, I repeat again, angle TQP equals to angle SLP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we can write down that angle QTP is equal to this angle, that is actually angle LSP. I repeat again, angle QTP equals to angle LSP, they are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle, angle theta, is a common angle that belongs to both triangles, so angle theta equals to itself. So we can define angle theta as angle TPQ is equal to angle theta itself, that we can define it also as angle LPS. Repeat again. Here, angle theta equals to itself. It's a common angle that belongs to both triangles. So we actually proved that the big right triangle TPQ is similar to the small green right triangle LSP according to angle similarity rule. And for the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will conclude that TP over SP is equal to QP over LP. Repeat again. We derive that TP over SP equals to QP over LP. So here TP equals to A according to what we have already found out. So we substitute TP by A over SP. SP equals to 6 units according to what is given as the question. So we substitute SP by 6. And it is equal to QP. QP equals to 5 plus 6, that is 11. Therefore, we substitute QP by 11 over LP. LP, it is the diameter of the circle that is equal to B. So we substitute LP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. Here we cross multiply this equation number 1, and we will get that according to equation number 1, A times B equals to 6 times 11 is 66. So AB equals to 66 according to according to equation number 1. So what is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of rectangle ABC times the width. The length is AB times the width is BC. We have already found out that AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that the area of rectangle ABCD equals to 66, but according to equation, the area of rectangle ABCD equals to A times B. But according to equation number 1, we found out that AB equals to 66. So we can write here that AB equals to 66. So in conclusion, we found out that the area of triangle ABCD equals to 66 square units. We finish with the second method. In the next step, I will summarize the lecture. We'll start with the first question. So, in the drawing, we have triangle ABC. Inside triangle ABC, we have this circle that is described by triangle ABC. Side BC equals to 2 units. Angle ABC equals to 6 degrees. Angle ACB equals to 75 degrees. And our mission is to find out the radius of this circle that is inscribed by triangle ABC. So, In the first method, we did a construction. From point C, we draw perpendicular on AB, so this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Then I copied the right green triangle DBC in a new page, and we analyze triangle DBC. This is the right triangle DBC that I copied from the original drawing. Here, in the right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have in triangle DBC? This angle equals to 60 degrees, plus this angle that is equal to 90 degrees, plus the missing angle that we defined as x. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 60 degrees plus 90 degrees is 150 degrees, and 150 degrees plus x must be equal to 180 degrees. Here we subtracted 150 degrees from this equation and found out that angle x, the missing angle x, equals to 180 degrees minus 150 degrees, it is equal to 30 degrees. Then we continue to focus on the right triangle DBC. In the right triangle DBC, here this angle equals to 30 degrees, okay? In the right triangle DBC, sinus 30 degrees equals to dB over BC. Sinus 30 degrees equals to dB over BC. So sinus 30 degrees is 1/2. That is equal to dB, and BC is 2, so we substitute BC by 2. So 1/2 equals to dB over 2. We multiply this equation by 2, and we found out that dB equals to 1 unit. Here, dB equals to 1 unit. We continue to focus on the right triangle DBC. In the right triangle DBC, cosine 30 degrees equals to DC over BC. Okay, so cosine 30 degrees equals to DC over BC, and BC is 2, so we substitute BC by 2. Cosine 30 degrees is square root of 3 over 2, so square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and found out that DC equals to square root of 3 units. Here, DC equals to the square root of 3 units. Okay, then we found out the size of this angle, angle ACD. Angle ACD equals to the big angle that is 75 degrees minus the small angle that is 30 degrees. 75 degrees minus 30 degrees equals to 45 degrees. Then I copied the right triangle ADC in a new page, and we analyze triangle ADC. In triangle ADC, we have this angle equals to 45 degrees, this angle equals side DC equals to square root of 3 units. So we know that the sum of the angles in the right triangle ADC is equal to 180 degrees. That is to say, this angle equals to 90 degrees, this angle equals to 45 degrees, plus the missing angle. In total, the sum of those three angles must be equal to 180 degrees. So here, 90 degrees plus 45 degrees is 135 degrees, and 135 degrees plus x in total must be equal to 180 degrees. We subtracted 135 degrees from this equation and found out that the missing angle, angle x, equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. So those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of this angle, we have side DC. In front of this angle, we have side AD, and those two sides that are located in front of equal angles must be also equal to each other. That is to say, AD must be equal to DC. Okay, but we already found out that DC equals to the square root of 3 units. So we can write here that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units, we will derive that AD is also equals to square root of 3 units. Here, AD equals to the square root of 3 units. Then we implemented the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, the square of the apotropes equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. AD equals to 3, therefore AD square is 3 squared, that is 3. DC equals to square root of 3, therefore square root of 3 square is 3. So in conclusion, we found out that AC square equals to 3 plus 3, that is 6. We took out all of this equation and found out that AC equals to the square root of 6 units. here AC equals to the square root of 6 units. Then I presented to you a new formula that helps us to find out the radius of any circle that is described by a triangle. According to the new formula, the radius of a circle that is described by a triangle will be equal to the area of the triangle over the semi-perimeter of the triangle. We implemented the new formula in our drawing. So in our drawing, the radius of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of triangle ABC. And the semi-perimeter of any triangle is equal to the perimeter over 2. Okay, so the area of the radius of this circle that is described by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC equals to the base of the triangle times the height over 2. The base of the triangle is AB. The height to the base is DC over 2. AB equals to 1 plus square root of 3. DC equals to square root of 3 over 2. So this expression 1 plus square root of 3 times square root of 3 over 2 is 2.366. So the area of triangle ABC equals to 2.366 square units. And the same perimeter of triangle ABC equals to the perimeter that is AB plus BC plus AC, and if we divide the perimeter over 2, we get the semi-perimeter. AB equals to 1 plus square root of 3, BC equals to 2, AC equals to the square root of 6, all divided by 2. This expression equals to 3.59 units, so the semi-perimeter of triangle ABC equals to 3.59 units. Therefore, the radius of this circle that is described by triangle ABC will be equal to the area of triangle ABC over, that is 2.366, over the semi-perimeter of triangle ABC, that is 3.59. 2.366 over 3.59 equals to 0.6589 units. So we found out that the radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first method. Then I presented to you how to find out the radius of this circle that is described by triangle ABC according to the second method. In the second method, we define the center of the circle as point O. We define the point of tangency of tangent BC with this circle as D. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself. This is exactly the definition of a radius, that is to say, OD is the radius of this circle, we defined it as R. We have here the radius OD that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and B together by a straight line, we join points O and C together by a straight line. We define the point of tendency of tangent AB with this circle as E. We define the point of tendency of tangent AC with this circle as F. We join points O and D together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle that is equal to R. We have the radius OE that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and F together by a straight line. Again, point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. So we have the radius OF that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, the lengths of those two tangents are equal to each other, that is to say PA is equal to PB. We implemented rule number 2 in our drawing. In our drawing, we have the common external point B. From the common external point B, we have tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, tangent BD is equal to tangent BE in its length. Likewise, from the common external point C, we have two tangents to the second, tangent CD and tangent CF, and according to rule number 2, they are equal to each other. That is to say, CD equals to CF. Then we proved that the green triangles can go into the orange triangle. Why those two triangles can go into each other? First of all, BD equals to BE according to rule number 2. In addition, DO equals to OE, they are both the area of the circle, therefore they are equal to each other. And finally, side OB is the common side that belongs to both triangles, so side OB equals to itself. So we proved that those two triangles can go into each other according to side rule, therefore those two angles are equal to each other according to the rule that the corresponding angles in congruent triangles are equal to each other. So if we define one angle as alpha, then the other angle must be also equal to alpha because of the fact that they are equal to each other. So here we have the sum of those two angles is alpha plus alpha, and alpha plus alpha equals to 60 degrees according to what is given as the equation. So 2 alpha equals to 60 degrees, we divided the equation by 2 and found out that alpha equals to 30 degrees. So this angle equals to 30 degrees and this angle also equals to 30 degrees. Then it is very easy to prove that those two triangles are also equal to each other according to side rule. Therefore those two angles are equal to each other according to the rule that the corresponding angles in congruent triangles are equal to each other. So if one angle is equal to theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. So the sum of those two angles is theta plus theta, and theta plus theta equals to 75 degrees. So here we divided this equation by 2 and found out that theta equals to 37.5 degrees. This angle theta equals to 37.5 degrees, and this angle theta equals to 37.5 degrees. Then we focus on the green triangle OBD. On the green triangle OBD, tangents 30 degrees equals to OD over DB. Okay, here tangents 30 degrees equals to OD over BD. OD equals to R, so we substitute OD by R. So in conclusion, we found out that tangents 30 degrees equals to R over BD. We multiplied this equation by BD and then we divided it by tangents 30 degrees, and in conclusion we found out that BD equals to R over tangents 30 degrees. Then we focused on the yellow triangle ODC. The yellow triangle ODC, tangents 37.5 degrees equals to OD over DC. And tangents 35 degrees, tangents 37.5 degrees equals to OD over DC. OD equals to R. Therefore, in conclusion, we found out that tangents 37.5 degrees equals to R over DC. We multiply this equation by DC and then we divide it by tangents 37.5 degrees, and in conclusion, we found out that DC equals to R over tangents 37.5 degrees. We know that DC is equal to DB plus DC. Here BC equals to DB plus DC. Here BC equals to DB plus DC. BD equals to R over tangents 30 degrees. DC equals to R over tangents 37.5 degrees. We took a common factor. We know that BC equals to 2 units. We took R as a common factor out of those two expressions. So what is left from R over tangents 30 degrees after we took from it R as a common factor? What is left is actually 1 over tangents 30 degrees. What is left from this, from R over tangents 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over tangents 37.5 degrees. So here 1 over tangents 30 degrees equals to 1.732. 1 over tangents 37.5 degrees equals to 1.303. So 2 equals to R, and 1.372 plus 1.303 is 3.035. We divided this equation by 3.035 and found out that R equals to 2 over 3.035, and it is equal to 0.6589 units. So in conclusion, we found out that the that the radius of this circle that is described by triangle ABC equals to 0.658 units. Okay, then I presented to you the second question, and we solved the second question in two different methods. So in the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle that is described by rectangle ABCD. Chord SP equals to 6 units, line segment SQ equals to 5 units, and our mission is to find out the area of this rectangle ABCD. So we know that all the angles inside the rectangle are right angles, therefore those 4 angles are all right angles. We define side AB as A, we define side BC as B, and we know that BC is also the diameter of the circle, so I wrote it here. And then we define the center of the circle as point O. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that we define as R. If the diameter equals to B, then the radius must be equal to B over 2. So R equals to B over 2. Then I presented to you rule number 4. According to rule number 4, whenever you draw from the center of the circle perpendicular to any chord, this perpendicular bisects the chord. So we have here perpendicular OM, and according to rule number 4, the perpendicular OM bisects chord SP, that is to say SM equals to MP. So if SM equals to X, then MP must be also equal to X. So here SM equals to X and MP also equals to X. X plus X is equal to SP, that is to say 2X equals to SP. Here SP equals to X plus X, so 2X equals to SP, but according to what is given as the question, SP equals to 6. So for this equation, 6 equals to SP equals to 2x, we derived that 6 equals to 2x, we divided this equation by 2 and found out that x equals to 3. Here x equals to 3 and x equals also to 3. Then we join points O and F together by a straight line. Point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of this circle. We have the radius OF that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So inside quadrilateral OPFC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. Okay? Then from point Q, we draw perpendicular on BC. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our definition. We define the touching point of the perpendicular from point Q and BC as T. So here we have quadrilateral OPLT that has 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral OPLT we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral OPLT as a rectangle. Quadrilateral OPLT is a rectangle, but we know that the opposite sides of a rectangle are parallel to each other. That is to say all OP is parallel to LT. OP is parallel to LT. But OP, here LT is part of perpendicular QT. And QT is a perpendicular, it is absolutely a straight line. So QT is a straight line. So LT is part of the straight line QT and is parallel to OP. So if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. That is to say, the straight line QT must be also parallel to OP. QT is parallel to here. QT, LT, here we have, therefore QT is parallel to OP. Okay, you can derive from it that QT is also parallel to OP. Okay, QT is also parallel to OP. QT is also, the side line QT is also parallel to OP. And we have here rule number 9 that alternating angles between parallel lines are equal to each other. Those two angles are defined as alternating angles and are located between the parallel lines OP and QT, therefore they are equal to each other. Okay, so angle OPQ is equal to angle PQT. So if we define angle PQT as theta, then from this equation we derive that angle OPQ is also equal to theta. This angle is also equal to theta. Okay, then we focused on quadrilateral QT DC. In quadrilateral QT DC we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore in quadrilateral QT DC we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate quadrilateral QT DC as a rectangle. Quadrilateral QT/DC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, QT equals to DC. QT equals to DC, but ABCD is a rectangle, and we know that the opposite sides of a rectangle ABCD are equal to each other. That is to say, DC equals to AB. Here, DC equals to AB. And from this equation, QT equals to DC equals to AB, we will derive that QT is also equal to AB. But according to our definition, AB equals to A. So we can write here that AB equals to A. And for this equation, QT equals to AB equals to A, we will derive that QT is also equal to A. Here, QT is also equal to A. Okay, then we focused on the right small triangle OPM. So I copied the right small triangle OPM. This new page is the right triangle OPM. This is the right triangle OPM that I copied from the original drawing. The right triangle OPM, cosine theta equals to PM over PO. Cosine theta equals to MP over OP. MP equals to 3, OP equals to B over 2. So 3 over B over 2 is 6 over B. So according to equation number 1, we found out that cosine theta equals to 6 over B. Then we focus on the right big triangle, triangle QPT, and on the right big triangle, triangle QPT. Cosine theta equals to QT over QP. Okay, cosine theta equals to QT over QP. QT equals to A, and QP equals to 5 plus 6, that is 11. Okay, so in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. So we have two different expressions for cosine theta, therefore we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 equals to 6 over B, and it must be equal to cosine theta according to equation number 2 that is equal to A over 11. So according to equation number 3, we found out that 6 over B equals to A over 11. We cross multiply this equation number 3, and we found out that AB equals to 6 times 11 is 66. So AB equals to 66. And what is the area of rectangle ABCD? It is equal to the length times the height. The length is AB, the height is BC. AB equals to A, and BC equals to B according to our definition. Therefore, we found out that the area of rectangle ABCD equals to AB. But we just right now found out that AB equals to 66. So we can write here that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. We finished with the first method, and I presented to you the second method to find out the area of rectangle ABCD. In the second method, we know that all the angles inside the rectangle are right angles, so those 4 angles they are all right angles. We define, as we did in the first method, AB as A and BC as B. BC is also the diameter of the circle, so I write here that BC is the diameter of the circle. Then we define the center of the circle as point O. We join points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself. Therefore, OP is the radius of the circle that we defined as R. But the diameter is B, therefore the radius must be equal to B over 2. Half of it, that is B over 2. So R equals to B over 2. Okay? Then we extended the radius PO until it intersects with side AD at point T. Inside quadrilateral ABTP we have 1, 2, 3 rectangles. Here, I didn't mention it, that OP is the radius that is drawn to the point of tendency. Therefore, this angle equals 90 degrees and this angle equals to 90 degrees according to rule number 1. So inside quadrilateral APTP we have 1, 2, 3 right angles. Therefore, the fourth angle, this fourth angle must be also equal to 90 degrees. So quadrilateral ABTP has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral APTP as a rectangle. Okay, quadrilateral ABTP is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB is equal to TP. Okay, AB equals to TP, but AB equals to A according to our definition. So from this equation, A equals to AB equals to TP, we derive that TP is also equals to A. Likewise, inside quadrilateral TPDC, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. Okay, then we join points L and S together by a straight line. What is the definition of chord LP? Chord LP passes for the center of the circle, therefore it must be the diameter of the circle, according to the rule that any chord that passes for the center of the circle must be the diameter of the circle. So LP is the diameter of the circle, that is equal to B. By joining points L and S together, we created here peripheral angle LSP. Peripheral angle LSP rests on LP, that is the diameter of the circle, therefore it is equal to 90 degrees according to rule number 5. So we define this angle as theta. So in the green triangle LSP, this angle equals to 90 degrees. This angle equals to theta, so this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90. 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Okay? For the same reason exactly, in the big triangle, the big right triangle TPQ, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we proved that the big triangle, triangle QTP, is similar to the small green triangle, triangle LSP. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, angle theta is a common angle, so angle theta equals to itself. So we proved that those two triangles are similar to each other according to angle similarity rule, and from the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that TP over SP equals to QP over LP. Here, TP equals to A. We substitute TP by A. SP equals to 6. We substitute SP by 6. QP equals to 5 plus 6, that is 11. So we substitute QP by 11. And finally, LP equals to B, that is the diameter of the circle, so we substitute LP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. We cross multiply this equation number 1, and we found out that A times B equals to 11 times 6, that is 66. So AB equals to 66 according to equation number 1, and the area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width, that is BC. AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that the area of rectangle ABCD equals to AB. But we just right now found out that according to equation number 1, AB equals to 66. So we can write here that AB equals to 66. And finally, we found out that the area of rectangle ABCD equals to 66 square units. So in both methods, we found out that the area of rectangle ABCD equals to 66 square units. And in the first equation, in both methods, we found out that the radius of this circle that is described by triangle ABC is equal to 0.6589 units. Okay? Thank you very much.